nucleophile you use, in some cases, the reaction will stop at the nucleophilic addition stage. Like when water is nucleophile, okay, the reaction will stop at the, hydrate, which is the geminodiol. Okay? Or if the hydrogen cyanide is the nucleophile, the reaction also going to stop at the addition product stage. You see the cosine or hydrogen. Okay? But when we have amine as a nucleophile, the reaction doesn't really stop at the addition stage. And for instance, we're gonna use one, the amine as example. Say we have just a methylamine, okay. Name, you don't need to worry, okay. So, if it react with say acetone, assume the reaction happen in a very acidic environment, slightly acidic environment, okay. So the nitrogen will be nucleophilic attack carbonyl carbon, and then the CO pi bond will break, and that's in in the nucleophilic addition stage, this reaction is considered to be this elementary step is considered to be rate limiting. Okay, just keep in mind about the formal charges. Okay, so obviously we have 2 additional protons here. Okay, then you have a proton transfer. Okay, which I'm not gonna go through all the details. Okay, you will get this. You don't need to worry about the name. Basically, it's the nucleophilic addition product. I'm not gonna tell you name. As long as you know the proton add to the carbonyl oxygen, the nitrogen nucleotide added to the carbonyl carbon. Then, see, in this stage, the reaction is limited by, how well the amine can use its nitrogen nucleophilic attack, the carbonyl carbon. Then in second stage, if assume the reaction is happens in a slightly acidic environment, say we have a bit slightly acidic environment, it's important to, why I would say only slightly acidic, because if the environment is not a slightly acidic, if highly acidic, reaction actually will not proceed well. Okay, and I will quickly explain that. And give you water. Okay, and then in the second stage, this you're gonna have this rate limiting step. The CO bond breaks. Give you the carbocation plus water. Okay, but this carbocation, okay, is no conventional carbocation. Under the know that this positive charge carbon is next to a lone pair bearing nitrogen atom, and this nitrogen atom has extraordinary ability to stabilize the positive charge by donating electrons here. Why I'm saying extraordinary? Because nitrogen is the out of second period elements that can have the lone pair nitrogen is probably the least electronegative one. Okay, typically you see nitrogen, oxygen, fluorine, they can carry a lone pair, right? Out of those, atom, nitrogen is the least electronegative one, so it has the strongest desire to give out this lone pair. So that makes this carbocation extraordinarily, this type of carbocation extraordinarily stable. Okay? It's significantly more stable than the kind of carbocation we have seen earlier. This carbocation is already more stable than typical, say, tertiary carbocation or even allylic carbocation. If you have the lone pair bearing oxygen atom, you can have this. So the right side of carbocation is already considered to be more stable than tertiary and allylic in general. Okay, so the left side one even more stable than the right side. Okay, and because nitrogen is less electronegative. So there's a consequence of such a high stability. But what you can see is here, if you look at this mechanism, okay, for second stage, we can treat it as it's E1 elimination, because then you can have water, okay, to come to take this proton, okay, away. Give you the hydronium ion and the imine product. Okay, that's kind of E1 elimination. And this E1 elimination, because of it involves the formation of a carbocation, and according to this mechanism, this carbocation formation is catalyzed by the hydronium ion. Okay, so for the second stage reaction, an acidic environment would help the second stage reaction to go faster, because the second stage reaction is catalyzed by an acid. Does it make sense? Because an acid will, encourage the carbocation formation, so can make the carbocation formation is the rate limiting step. Therefore, the entire elimination process will be faster. So logically, the second stage will proceed faster in a more acidic environment. Okay, but what about the fourth stage? So the second stage, because of the the formation of carbocation is rate limiting, and this formation of carbocation need assistance of acid. So acidic environment is good for second stage. Okay, so this elimination is faster in a more acidic environment. What about the first stage? First stage. To answer the question about first, yeah. Huh? Water? What about the first stage? If you have a more acidic environment, how about you think the first stage will be faster or slower if you have an acidic environment? Let's say you have 0.1 m sulfuric acid in the system, the pH about 1. Okay, so do you think the first stage will be faster in acidic environment? Slow. Why slower? If you look at first stage, okay, look at the mechanism I written here. The rate limiting step is amine attacks the carbonyl. So under no circumstance from here to here, the acid is never involved. Okay, so acid does not help first stage. And actually, Karina, what you said is correct. If acidic, the first stage will be slower. But why? That is because the acid-base property of amine and alcohol, they are different. Okay, so we can just we can using water to approximate amine, and using ammonia to approximate using water to approximate alcohol. Okay, because what is alcohol? You can using an alkyl group replace hydrogen in water, right? So this is the water, right? You replace this hydrogen with an alkyl group, you have alcohol, right? So we can use water to approximate alcohol and use ammonia to approximate amine. So I hope you guys recall water, its conjugate acid is hydronium ion, okay? And the conjugate acid of ammonia is ammonium ion, okay? And the pKa of hydronium ion, maybe you guys don't remember, it's about minus 1.5, okay? About, okay? And the pKa of ammonium ion, do you have anyone has a roughly idea? Just guess. Higher than, you see pK should be higher than hydronium ion or lower than hydronium ion? Huh? 200? Higher, okay? Higher because we know these two chemical species are directly comparable. They are a single positive charge. All consist of hydrogen bound to the second period element. Okay, so their acidity is judged by polarity of the breaking XH bond. And OH bond is more polar than NH bond. So that's why hydronium ion should be substantially more acidic than ammonium ion. How much more acidic? I'm not asking to memorize, but I just give you a number. The pKa is about 9. Okay, so it's like 10 to 11 orders magnitude less acidic than hydronium ion. Okay, so what is the consequence here? If you place the ammonia, okay, amine, okay, in an acidic environment, this equilibrium constant will be roughly 10 to the 11th order of magnitude, 10 to the 11th. That means that if you put the amine to acidic environment, the nitrogen lone pair will be fixed by protonation. See, once amine is protonated, okay, this guy can this guy still serve as a nucleophile? The protonated amine, no lone pair available, so can't serve as nucleophile. Okay? So that's why, as Karina said, for the first stage reaction, if you make the reaction environment more acidic, then actually will make it slower, because if you make it acidic, then the nucleophilic amine, the real effective concentration of nucleophilic amine will be substantially lower. Okay, so the reaction will not happen if really acidic environment. So, but the acidic environment is good for second stage. So if you really look at this imine formation reaction, the best pH value will be such that close to neutral, because in that case, this one goes reasonably fast. Second stage also reasonably fast. So somewhere around 6 is the fastest for overall reaction, because this reaction has 2 stages. Okay, if pH value too high, second stage will be slow. Okay, if pH value too low, first stage will be very slow. Okay, so that's why around pH 6 is the fastest for this kind of reactions. Okay, now a related topic, under the last class, I did give you an example of, let's say we have this amine, okay, and this ketone, okay, and if we have this amine, if directly mixing these two things without adding any catalyst whatsoever, and basically you are looking at the right side of reagent has 2 kinds of nucleophilic atom, nitrogen and oxygen. So the both types of nucleophilic atom could attack a carbonyl carbon. The real product will depend on which attack is faster. Okay, so in this case, do you think nitrogen will be the effective nucleophilic atom attacking carbonyl carbon or the oxygen will be nitrogen, because both nitrogen and oxygen has a lone pair available, but nitrogen has a low electron activity, so it basically it holds its own lone pair weaker than oxygen. They have stronger ability to give out. Okay, so that this will give you the product of amine attacks. Okay, give you this one. Okay, so that's what we talked about last class. Okay, now let me change the reaction condition a little bit. Okay, now assume we put 1.1 molar equivalent, okay, of TSOH. And the TSOH is a kind of organic sulfonic acid, okay, and is basically this one. It's a strong acid, okay, strong acid catalyst we mentioned in the earlier chapter. Okay? In this case, what will be happening? Okay, this important 1.1 molar equivalent. Okay, so that means something will be protonated. What will be protonated? The N will be protonated because that's the most basic atom here. Okay, so the basically this reagent effectively become the let's say effectively become so in this case, then the nitrogen can no longer be nucleophilic because it's fully protonated. So the only nucleophile you have there is the oxygen. Okay? And now the alcohol, as we know, can react with carbonic under acid catalyst because we 1.1 molar equivalent, still 0.1 molar equivalent acid is left over to serve as a catalyst. Okay? So this reaction will be the lead to the these two oxygen attacking the carbonyl carbon. So you will be getting a compound eventually you have the kind of keto formation, because this keto formation is thermodynamically preferred because this keto give you a highly stable 6-membered ring. Okay? So this you see the same two compounds react. If you change pH value, the reaction can be switched. Any questions? Yes?
So since the nitrogen is fully protonated, the oxygen becomes a nucleophile, right?
Yeah, because of the if it's in the absence of the acid, okay, nitrogen is more nucleophilic. Okay, it will be doing its nucleophilic attack faster than oxygen does. But if nitrogen is protonate deactivated, so then that's the only thing oxygen will be left doing nucleophilic attack. And this is kind of also pretty common thing if you want to selectively see if you are facing a compound that has both nitrogen and oxygen atom. If you want the O to do the nucleophilic job, then you can protonate the nitrogen so that deactivate the nitrogen. Only O will be doing the the nucleophilic attack. Yeah.
From this part, can we go back to aldehyde?
Going back.
Go back to aldehyde ketone.
Oh yeah, you can doing the the doing same thing, add acid and a lot of water. Yeah, you certainly can do that. It's just like acetal to the carbonyl conversion. Okay? You put tons of water there, acid. Yes, go back to aldehyde ketone.
And that's usually done for protection, right?
Yeah, when you basically want to be protected. Okay. Any other questions? So in general, if you have the say X, Y ketone or aldehyde, if you have NH2 group, whatever here, it doesn't matter that much, okay? Because usually whatever group here will be less nucleophilic than the amino group here, okay? Usually, okay? So you will get to, the X and the Y, you will have this imine, okay? Imine type of structure. That's the general for all the compounds with NH2 groups. Okay? Now, what if we have a secondary amine react with the carbonyl? Okay. So the first stage is still same, because when you look at the amine, you always can read, you can interpret, you can basically break down the amine as the combination of the electrophilic proton and the nucleophilic amide part. You always can read that, okay? So in the first stage, nucleophilic addition, the proton always should go to the carbonyl oxygen, and the amine, the nitrogen, and the whatever group attached to nitrogen will be attached to the carbonyl carbon. And then the second stage still will be, the elimination. But, as we're gonna see, because of the, you don't have a NH bond on this nitrogen anymore, okay? So elimination will not be happening on this nitrogen because you don't have because if you recall that the second stage is E1 elimination, right? You need to remove a beta proton. And if you do have a beta proton on nitrogen, that's most acidic proton to be eliminated. So you will eliminate that one, okay? But if you have a secondary, start with secondary amine, means you have 2 carbon on it. So there's no NH bond. No NH bond to eliminate it. So you will eliminate one of the, the proton from the beta carbon. You will get something called enamine, okay? Means enamine is a CC double bond direct bond to nitrogen. En means alkene. Amine is means something single bonded from carbon to nitrogen called enamine. Okay? So the enamines are actually mildly nucleophilic at the carbons, so they can actually pretty useful for carbon bond formation reactions. And this probably we will not talk about too much, but we might look at this at the later part of the chapter. Okay, but let's see how does enamine work. Okay, so for the nucleophilic addition part, it's all the same story. I'm not gonna repeating it. Okay, it's exactly the same as the primary amine. Okay, but for the elimination part, and I already showed you a mechanism if the reaction, elimination stage, if the reaction happens in a weakly acidic environment, okay, how did the reaction happen? If the weakly acidic environment, the nucleophilic addition product, the OH group will be protonated by hydronium ion. You have a good leaving group, water can leave, okay. And but what if the reaction system is not weakly acidic, say weakly basic, okay? And if it's weakly basic, actually you are seeing a first example where the hydroxide ion, okay, can directly leave. See, this is called hemiamino, is basic nucleophilic addition product. Hydroxide can directly leave, give you a carbocation. So why hydroxide can live here? We know hydroxide is a bad leaving group, okay? In organic one, we discussed extensively. Say hydroxide is bad leaving group, but at that time I already told you it's not an impossible leaving group. Under special circumstance, it could, the leave, okay? So what drives the leaving of the hydroxide ion is because if the hydroxide leave, you actually have a CN double bond here. Okay, CN double bond. Well, it's kind of similar to a CO double bond. It's a bit weaker than CO double bond, but stronger than CC double bond. Okay, so this is actual bond formation make the hydroxide ion capably leaving. And this guy, we probably can also look at the other resonance form of this guy. Is the basically. So it's a carbocation, okay? But this carbocation, as I said, is an extraordinarily stable type of carbocation, okay? More stable than tertiary, more stable than allylic, more stable than oxygen-stabilized carbocation. It is so stable, it mostly can be viewed as a compound with CN double bond, okay? So that's why hydroxide could leave. Okay? And you will see a similar situation later on in chapter 20, okay? And hydroxide can also leave if a carbonyl group can form as a result of the leaving, okay? Because of the CN double bond is just a little brother of CO double bond. CO double bond is a very stable, one of most stable double bonds you can have, okay? But CN double bond, the little brother of CO double bond, it is more stable than the CC double bond. Okay, CC double bond is the say youngest sibling. It's a very weak double bond. Okay. And then because this guy is a carbocation, okay, so you can look at, okay, if you have a carbocation, I could have a beta elimination from this carbocation. So if this is a carbocation, this is alpha carbon, okay? So you could remove a proton from beta atom. Atom is beta to it, okay? So how many beta atoms do you have here? You have a hydrogen, okay? You have a hydrogen, you have a nitrogen, and you have a carbon, okay? And how many beta proton you can have? There's only one beta proton here because this is alpha proton. So there's no proton on the nitrogen. So only this proton can leave, okay? So this gives you something called in amine. Okay? So you can think about it if the nucleophilic addition product of amine to carbonyl wants to undergo elimination. If there's an NH bond available, you will always lose that proton because that proton is more acidic than the CH bond. But if no NH bond there, then you will just the removal proton from the the beta carbon. Okay, so that is the mechanism. Okay, and similarly, if this reaction happens in acidic environment, then the elimination mechanism will be same as what we have seen here. Okay, step 3, step 4, step 5. If it's acidic environment, same as we see here. Okay. But anyway, let's look at the just look at a few examples. Okay, 2 examples about the reaction. The product is the same, but the mechanism different. Yeah. Say if we have let's say we just heat it, okay? And in this case, your first step product should be this. Then you can have a beta elimination reaction, take it with here, okay? And you get to the Now, if we do it slightly differently, although the reactant will look very similar, okay, reactants look very similar. Still, we do heating, okay. So what will be happening is first stage, you're gonna have the nucleophilic addition. Okay. But the problem is now there's a no NH bonds available. So we know this one gonna be alpha carbon. Okay. So you have to remove a proton from beta carbon. So what is beta carbon? Those two are the possible beta carbons. Okay. So you're gonna eliminate one of proton on that beta carbon together with OH group. So minus water. Okay. You will get to the that's what happens if you have a secondary amine. Okay. Now amine, when amine react with the carbonyl, you will be see. Oh, first you have addition. Second, you have elimination. Okay. So the last kind of nucleophile we will be seeing also can react with carbonyl. Its reaction is slightly different. It is a kind of nucleophile. Still, the reaction can be analyzed by traditional nucleophilic addition, but you will add some additional twist will be added to the reaction. So the product is technically still it kind of is addition followed by elimination. Still is addition followed by elimination, but it has some additional twist. So but the reaction overall you can see it's similar with a primary amine react with carbonyl. If you have primary amine, just let me write down here. If you have a primary amine react with carbonyl, right? NH2 a group, okay? What you'll be seeing eventually you get to R prime carbon and a nitrogen and a G, okay? So that's you have a primary amine, okay? So it's addition followed by elimination. But if you have a special kind of nucleophile, is a carbon-based nucleophile, and the structure is showing here. This kind of nucleophile we call elide, okay? And this elide feature a carbon phosphorus bond, and the carbon is somewhat more electronegative than phosphorus. So this carbon phosphorus bond, the carbon is typically the negative polarized. Okay, so in this compound, the nucleophilic atom is carbon. It's relative not that common because most of time when we have carbon heteroatoms, the carbon heteroatom bond will make the carbon positive polarized in most of the cases. Okay, but the phosphorus because somewhat less electronegative than carbon, so this actually is provides a nucleophilic carbon. Okay, so then this nucleophilic carbon will be bound to the electrophilic carbon, then followed by elimination will give you alkene product. Okay? So it can be viewed similar to this, the primary amine and the carbonyl reaction. Okay? But the elimination is a slight different. Okay? We will look at it. Okay? So the Whittaker reaction is you know for when it has the important synthetic value, can give us you know an approach to synthesize alkenes, you know with well-defined substituents on the CC double bond. Let's say if we want alkene with R prime, A and B, 4 groups attached to the CC double bond. Okay, we can actually you know make this alkene by you know the reaction of aldehyde and ylide. Okay, so this is a one combination. Basically, can cut off the CC double bond and treat the left side come from a carbonyl compound. Okay, and the right side from ylide. Okay, or you can do the other way as well. So you can say, okay, I say the right side 2 groups is from the carbonyl, okay, and the left side 2 groups, you know they are from ylide, okay. So this is a major value of the you know the of the this Whittaker reaction. Okay, so the most of ylide we're dealing with, you know, has a phosphorus atom. One side connect to 3 phenyl groups. So let me just give you one example of ylide. I'm going to draw the full structure of a typical ylide. Okay, say I'm going to have a phenyl ring. And also you can, you know, this guy has 2 resonance forms. One, two, three, four, five. Oh, I didn't draw the too much trouble. Let's say I just using pH to represent the phenyl group. That's the common practice. Save time. Okay, just for the sake of save time. pH means the phenyl group. pH, okay, equal to phenyl group. And the right side form is non-polar form. Left side form is polar form. Okay. So as far as come to contribution, this form makes you know the greater contribution because they have extra covalent bond. Okay, and do not worry about the phosphorus breaking. You know the exceed octet rule is capable of doing that because it's a third period element. Okay, no worry. Okay, but you know the fact you can write this resonance form, you know it's a carbon is a nucleophilic atom. Okay. Now let's look at the reaction mechanism. Okay. So the reaction mechanism start, okay, from the nucleophilic attack from this you know the ylide carbon to the carbonyl carbon. This is nucleophilic, this is electrophilic, no problem, they attack. Okay, so for if it's a typical nucleophile, you would expect, let me write down here, if it's a typical nucleophile as we have seen so far, say if it's R1 R Okay, if the typical, the nucleophile, okay, you expect, oh, the reaction gonna lead to, if typical nucleophile, as we have seen so far, water, ammonia, cyanide, that's what we're expecting, right? The nucleophilic atom, using its lone pair to donate to the carbonyl carbon, then CO bond breaks, give you this one. That's the intermediate you would expect from a typical nucleophile, okay? But this nucleophile is not a typical nucleophile. It has a phosphorus atom there. And the phosphorus, just like a sulfur, phosphorus is exceedingly oxyphilic. Means a phosphorus atom has a very strong affinity, is even greater affinity to oxygen atom than sulfur does. Extremely high affinity to oxygen atom because the phosphorus oxygen bond is a very, very strong bond. Okay, the why so strong? It's out of what I would like to explain here, but it's 500 something kilojoule per mole. It's very strong bond. You see, just for the comparison, a carbon-carbon single bond is only 300 something kilojoule per mole. Okay, so this is a 500 something kilojoule per mole. Okay, exceedingly strong bond. So it's very large motivation, driving force for the phosphorus and oxygen bond to form. So actually, it doesn't give you the typical intermediate we have here. Instead, it forms a four-membered ring structure. Okay, that's the intermediate. Okay, why? Because very high phosphorus is very, very oxyphilic. So the driving force for the oxygen phosphorus bond form is exceptionally strong. Is beyond any single bond we have seen so far. Okay. Molecules are smart. This is a high stability can be gained from it. They will do it. Okay. Then again, because of extremely high, the oxy, the phosphorus being extremely oxyphilic. Okay. Then next step is like this. Okay. Because then you can have a phosphorus oxygen double bond. Okay. And eventually it's give you the product. Huh? Which one? Which arrow?
The arrow is pointing on the bond between oxygen and phosphorus. Goes to the oxygen.
Oh, you that's either way because that's two resonance forms. Either way, because oxygen also is okay. Basically, we'll see, but the key part is, this entire reaction. It's a special. What's the unique feature of the Whittaker reaction is phosphorus is highly oxyphilic. That's why its behavior is a little different from other things we have, the other nucleophile we have seen. So either way will be fine. But the key part is what you see in the product. You're gonna have the H, okay, and the POPH3, okay, and this one, if you like, of course, you can write it into other resonance form. Both are considered correct. Both are correct, okay? But obviously, left side making greater contribution because axial covalent bond. So the formation, this final product called phosphine oxide. Okay? You know it's considered very stable compound. So basically, if you do use phosphine in organic reaction, often the phosphorus atom in the phosphine will tend to take oxygen away from the other components, okay, to become the driving force of the reaction. Okay. So here, the Whittaker reaction driving force is the formation of this product, okay, have a phosphorus oxygen double bond. Okay. That's the major driving force of the reaction. Any questions here? It's just the twist, the extra twist we have here is the phosphorus being exceedingly, the oxyphilic. Yeah, the slide I'm showing here is good to oxygen, but it doesn't matter because both are correct. Okay? Depending on which product you eventually getting. Here it's giving in ionic form or called dipolar form. But if you're giving in the neutral form, then the way I wrote is correct. Okay? But either way is correct. So the major value of the Whittaker reaction is making alkenes. Okay, so when we if you use the elimination reaction to making alkenes, always there's a selectivity issue because of elimination. Often you have a few possible beta protons potentially can be eliminated. Okay, but if you yes, there's selectivity there. You didn't know which product is the major product, but if you use Whittaker reaction, all the groups on the double bonds are completely predefined. Okay? So you don't have to worry about, oh, I can have this, I can have that. Only issues you may have a stereochemistry concerns. Okay? But usually you get the trans product, basically more stable. If a stereochemistry is of concern, then the more stable the product will be the major one. So if you have trans cis, then usually it's a trans. So let's look at one example how we're gonna use this Whittaker reaction to design the synthesis of alkene. Okay, so this alkene we can isolate we can mark the double bond first. Okay, this is double bond. Okay, so what are the 4 substitutes on the double bond? Is a phenyl group, C6H5 phenyl group, and the hydrogen. These two groups on the left, and the 2 hydrogen on the right. Okay, so these are the 4 groups. So this is basically either you can take the the 2 left side group from the carbonyl. So that is one possibility, and then to the 2 groups on the right side coming from the Eli. This is one combination, okay? And then or you can do other way around, okay? So I will say, okay, these 2 sides come from the what called carbonyl. So then that will be the formaldehyde, okay? And the right side, left side 2 guys, they are coming from Eli carbon. PH3, okay? Yeah, both combination will be okay, okay? Both combination will be okay. But if you're really gonna do it in a laboratory, you're probably gonna choose the lower approach, because the formaldehyde is a gas. Okay, may not be most convenient to work with. Okay, but but if you just need to answer a question, both approaches are going to be fine. Okay? Now the question is, how do we make those, elide? Okay, those elide usually they are made from the alkyl halide. Okay, so you will take alkyl halide, being secondary, primary, both are possible. Then you're gonna take that alkyl halide, react with triphenylphosphine. And triphenylphosphine is because of the lone pair on the phosphorus atom, it's a good nucleophile. It's even if based on periodic rules, should be even a better nucleophile than nitrogen counterpart, because the phosphorus has a lower electron activity than nitrogen, so its lone pair is more willing to give up. Okay. So this is actually a pretty good nucleophile. Then you can have SN2 reaction, give you the substitution product. But this one is not really the elide yet, because if you look at this product, neutral one react with neutral halide, alkyl halide, then the halide is considered anion here. So this whole thing, organic part, is a cationic species. Okay, so it can't be nucleophilic. So how do we convert to elide? Then you need to treat this one with a strong base to remove a proton from the carbon. Then you will get elide. What? Halide will be because this one is gonna have a counter. If it's strong base, you're gonna have a counter ion, cation. Okay, this cation can go with the halide. Will be, let's say, if you this is sodium ion, if it's sodium ion, right? If the counter ion is sodium, you're gonna sodium halide will be leave the system. Okay. Under this organic, this strong base that can remove this proton, typically is a conjugated base of DMSO. So how do you prepare conjugate base of DMSO? You can throw some sodium hydride into DMSO. Can throw some sodium hydride. Okay. Sodium hydride is a very, very strong, the inorganic base, because sodium hydride you can consider as consists of sodium cation and hydride anion. Okay, and the hydride anion is extremely basic because hydride anion is a conjugated base of hydrogen gas. Okay, hydrogen gas. If you ask yourself, its acidity should be exceedingly weak acidic compound, because only has a hydrogen bond. It's a completely nonpolar, and the bond is not weak. It's kind of very strong single bond. So that's why I make a sodium hydride as an extremely strong base. And you usually don't see its nucleophilicity because it always shows its basicity. Its ability, its desire to serve as a Bronsted base is just overwhelmingly strong than its desire to serve as nucleophile. So this is just the how you prepare the elide. Okay. So for instance, if we want to have the method, let's say if we want to have this guy, okay, if we want to prepare this one, okay, we can take a methyl iodide, okay, and treat with triphenylphosphine. Then this will give you methyl pH3 plus iodide. Okay. Then you can treat this one with a conjugated base of DMSO. And the base serve as one role here is the CH, the CH2, PPH3 positive. So you have a base here, takes this beta proton away, and this one come over here, okay? Give you the ELI. CH2, PPH3, then of course the base takes the proton away, and this one is the ELI. So that's the way how to prepare the ELI. Okay. I'm just showing you using one alkyl halide as an example. How do you prepare ELI? And the question about the last nucleophilic addition to the carbonyl. Again, it's just like amine to carbonyl. It's a nucleophilic addition followed by elimination. But the special character of this reaction is it involves 4-membered ring, because phosphorus just loves oxygen that much. Okay, you will grab oxygen given any removal of probability, will grab the oxygen, bound to it. Okay, it's 500 something kilojoule per mole. And many of your biology major, you probably have learned this, right? In biology, because the ATP is the energy currency in a biological process. Why ATP is so can be used as energy currency is related with the phosphorus oxygen bond. Okay. Anyway, any questions? If no question, we will look at the oxygen of aldehydes. Okay, so the aldehyde can be oxidized into carboxylic acid, and this reaction typically happens in aqueous environment, at least in the presence of water. It doesn't have to happen in aqueous solution, but at least water must be present. So here's just one example. You can treat aldehyde with chromic acid, you'll get the carboxylic acid. So mechanistically, it's believed that the hydrate of aldehyde is involved. So as we know, water can add to carbonyl group pretty quickly, especially if the reaction is not neutral, either in the presence of base or in the presence of acid. And when you treat aldehyde with chromic acid, obviously it's a highly acidic environment. So the hydration itself will be catalyzed by acid. Okay? So then if you have aldehyde in the presence of water, you are quickly in equilibrium of its hydrate. And this, the hydrate is a diol, and this equilibrium constant is close to 1. So the formation is not that difficult. And note that in a hydride, there's one hydrogen bound to the carbonyl carbon. This is important. Okay. So once you have this germinal diol, it's a hydrate of aldehyde, then you can react with chromic acid. Based on the same mechanism we learned in chapter 6, you can consider this is a kind of form of Fischer acidification reaction. So basically, chromic acid, you can view it as like this. Okay, this is a chromic acid. Okay, so this hydroxy group and basically gonna combine with the gonna be nucleophilic attack. Okay, this chromium. Okay, and then lose a water molecule, become the chromic acid. Okay, this is just like a Fischer acidification reaction. The Fischer acidification reaction, remember chapter 6, although I didn't talk about detailed mechanism, I emphasize that's a hydroxy will be nucleophilic attack the carbonyl carbon, carboxyl carbon. Here, same thing, the hydroxy will be attacking this chromium, okay? And then losing a water become chromate ester, okay? The next step is, because this whole thing, you know, we can treat this oxygen, okay, as alpha atom, and this whole thing is a leaving group, and then if this oxygen is alpha atom, this would be beta atom, and then this in the hydrated aldehyde, you have a available beta hydrogen. So then the water can come out, take this beta hydrogen away. This is an E2 elimination. As we analyze chapter 16, as we analyze back in chapter 7, organic 1. So this is a leaving group, okay? This is alpha atom, this is beta atom. Water comes in, take a beta proton away, and this one leaves, and they give you carboxylic acid. This is why, if you recall in chapter 16, when we discuss oxidation of alcohols, we say primary alcohol, if you do oxidation in aqueous environment, will go all the way to carboxylic acid. Because if the primary alcohol, first stage oxidation product will be aldehyde, okay? The aldehyde will be even more reactive than the original alcohol, and the aldehyde will be further oxidized to carboxylic acid because of aldehyde. If oxidation carry out in water, you have aldehyde can be converted to hydrate, and hydrate can be oxidized into carboxylic acid. Okay? And if you do the oxidation of a primary alcohol in an anhydrous environment, then you can stop at aldehyde stage, because if it's anhydrous, no water, right? The aldehyde cannot be converted to hydrate. Okay, so that's why you need to do the if you want to convert oxidized primary alcohol to aldehyde, you need to use PCC, PDC in a dichromethane environment. No water. Okay, so you can avoid the hydration of aldehyde, because hydration aldehyde give you a geminal diol, and the geminal diol can be further oxidized into carboxylic acid. And why ketone is not such a reaction doesn't happen with ketone, because ketone although also can be hydrated, okay? Then this hydrate can react with chromic acid, give you a chromate ester, and this reaction is reversible. But the chromic ester can no longer undergo elimination reaction, give you the further oxidation product, because you don't have any beta hydrogen here. Okay. So if you look at the ketone version of chromate ester, this is a beta carbon. Okay. This is a alpha, you know, the oxygen, and these are potential leaving group. Okay. But do you have any beta protons here? Zero. Okay. So the reaction cannot move further. Okay. So that's why ketones will not be able to oxidize. Okay. So in order for the carbonyl compound to be oxidized, you have at least one proton, one hydrogen connect to the carbonyl carbon. That's means it must be aldehyde, because it's the the final stage is elimination of that proton. Okay. Any questions about the oxidation of the aldehyde and the ketone? And the oxidation of aldehyde, alcohol and aldehyde can also happen in the biological system. So the obviously in a biological system we cannot throw in some chromic acid into the oxidation. So the in a biological system, often NAD plus is used as oxidant. Okay, and the reaction they must be catalyzed by enzyme. Otherwise, the reaction will be slow. Okay, so the relevant reaction, to most of people's not most some people's life is the how the the ethanol is the convert inside our body if you consume it. Okay, so the if you drink alcoholic drink, the active component ethanol will be first oxidized into acetaldehyde. Okay, and then the acetaldehyde can be further oxidized to acetic acid. And acetic acid is not it's not harmful compound, but this guy is pretty harmful. Okay, so the the how well you can sustain or how much you can the drink is really depend on your body's ability to oxidize the ethanol finally to the harmless acetic acid. Okay? So the this enzyme activity in everyone body is different. Okay, so the that's why different people have different ability to drink alcohol. But alcohol, as a scientific study has shown that drinking alcohol has zero advantage. Okay, zero advantage. So the that's what I know of. There's zero advantage. Other than maybe someone like it, but this has zero advantage. It's probably more harmful than some other addictive compound. But just I guess historical reason, the no government has been successful, in banning it. Anyway, last section is about the the spectroscopy analysis of aldehydes and the ketones, and really I'm gonna focus on the infrared part, and the NMR part is really not too much, but the infrared part is for aldehydes and the ketones. All of them have the carbonyl group. So you will see a very intense band, usually around 1700 reciprocal centimeter, typically a bit higher. Okay, typically a bit higher. And but the key part is intense band. You should never miss it. If you see a tiny band at around 1700, it could be noise. Okay, it has to be intense band. Okay, yes.
So should it always be lower than the functional groups to the right of it? Like, is that like a good measurement? Like the peak is lower.
Bigger. The peak must be if the not the if you have a carbonyl group, if your compound is a ketone aldehyde, if that peak at around 1700, either will be strongest or second strongest. If it's some tiny peak, it could be noise or something. Okay, must be. If it's a tiny peak around 1700, it's not identification of ketone aldehyde. Could be noise, or you have some impurity there. If either the strongest peak or second strongest peak. Because why? Because CO double bond is one of the most polar functional groups you can have. I'm not saying the most polar, but one of the most polar functional groups you can have. Okay? So if you cannot miss it. If it's a small peak, that could be impurity. Either the most intense one or second most intense one. So that's the first one about carbonyl group. Okay. Then how about aldehydes and the ketones? Can we resolve it? Distinguish aldehydes and the ketones from the its infrared spectroscopy? Actually, you can, okay? Because of the ketones and aldehydes. The biggest difference: aldehyde has this carbonyl CH bond. Aldehydes have this CH bond. So this bond is unique for aldehyde. And this bond, very luckily, have very, very signature absorption peak. And typically you won't see in any other compound. It will give you a pair of peaks, usually around one is about 2700, the other 2800. Okay. So this is a characteristic peak for aldehyde. You have a pair of peaks around, one is about 2700, the other called 2800. Okay, and if you coupled with a intense peak at about 1700, then you have a positive identification of aldehyde. Ketones don't have this pair of peaks. Okay, ketones do not have this pair of peaks. Aldehydes do. Okay, so if you doing the unknowns, check your infrared carefully. If you see carbonyl group, carefully check whether you have. See, if you have an intense peak around 1700, you know you have a carbonyl. Okay, then whether it's ketones or aldehyde, check that what at about 2700, 2800, what are the a pair of peaks that are medium intensity, usually is sharp. Okay, so why this peak appear at this range? Okay, actually was a puzzle me quite a little bit, until I read a literature. Okay, so if you really look at this CH bond, this carbon is what hybridization state? Carbonyl carbon is what hybridization state? sp2. Yes, I heard someone say loud to be correct. Okay, so if based on the knowledge we acquired in chapter 14, you would expect this CH bond somewhere above 33,000. Okay, correct? sp2 CH bond stretching frequency should be a bit higher than sp3 CH. Okay, but why it's so low? You must be, did I tell you something wrong? Okay. The key part is here. You have this oxygen also is sp2 hybridized. Okay, so it has the two lone pairs on it. Okay, so what happened is this this CH bond, okay, will be anti-parallel with one of the oxygen lone pairs because of both carbon and oxygen sp2 hybridized, right? Correct? So this one of these two lone pairs will be anti-parallel to this CH bond. Okay. So then look, if you apply molecular orbital theory locally, okay, this CH bond, okay, can have its anti-bonding orbital extended to this side. Okay, basically this is a lone pair here. Okay, this lone pair here. Okay. And this is say this CH bond anti-bonding orbital. Okay, and can they overlap? They happen to be parallel, right? So this lone pair is anti-parallel to this anti-bonding orbital of this CH bond. Okay, right? They are anti-parallel because this whole thing. Lone pair, and this bond, they're all planar. They are all planar. Okay, so this anti-bonding orbital, okay, will be parallel to this lone pair. So this lone pair can actually overlap with this anti-bonding orbital. So this oxygen lone pair can overlap with this anti-bonding orbital. So this basically there will be some overlap. Okay. So if the lone pair goes partial to the anti-bonding orbital, what happens to that CH bond strand? If lone pair partially goes into the anti-bonding orbital of this CH bond, so how does it impact the CH bond strand? Become weaker, because if you put electron in antibody orbital, antibody, if you put electron there, the bond becomes weaker. Okay? So that's why this CH bond stretching frequency are usually low. Okay? But why it have two? That's a more complicated phenomenon called 4D resonance. That's too much to talk about. But it's just it's because of this CH frequency often happens to be at the same frequency of the twice of some bending frequency. So they have kind of splitting called 4D resonance. Okay? But that's too much to talk about. But you can say just somehow this CH bond stretching split into two bands. You take an average, will be 2750. Okay? Average of these two bands, 2750. 2750 is much lower than what you expect, say 3100. Why is it so much? that much lower because of the lone pair from oxygen goes into the antibonding orbital. Okay, make it substantially lower than expected. Okay? Well, that's what just explained. But if you don't want to know why, at least memorize this. Okay, the aldehyde CH bond has a pair of absorption, medium intensity, sharp, around the one around the 2700, the other 2800.
And
If-
if it's a ketone, do they appear somewhere else? or
Ketone
not?
doesn't have it because of the no CH bond. Yeah. Ketone doesn't have it. Okay. Ketone, whatever remaining part, all just vanilla things like all those are sp3ch. Okay, you see something the band a little below 3000. Okay, that's vanilla. You have seen many times. Okay, and you see carbonyl, and this is aldehyde CH. Okay, so the you please. Yeah, let's tell you, I will test it in the next exam. And NMR, nothing unusual. If proton NMR, the aldehydes, if you do have aldehyde CH, you will expect the chemical shift value around the 10 ppm. We already explained in chapter 14 why that low chemical shift value, because carbonyl group very electron withdrawing, and also the pi bond, you have the you know this hydrogen also in the deshielding zone of the pi bond. And this is a aldehyde proton characteristic. And if you have a proton on carbon next to carbonyl, and this carbon, as we're going to see later on, this we call alpha carbon. Okay, if you have a proton alpha carbon, the chemical shift value generally around 2 to 3. Okay? This is something again related to the carbonyl, you know, related with the carbonyl group. Okay? So the just a bit relevant questions. Okay, so I just give you example. If you have this compound, okay, so this chemical shift value generally should be a bit lower than this chemical shift value, okay, because the CH3s, okay, generally are of lower chemical shift than CH2s. You can consider H is a little bit less electronegative than carbon, okay? A bit less electronegative than carbon. Okay? And this one, obviously, should be, if you ask, you guess the chemical shift value, what should be? 1 point, maybe 2, 1.1, something like that, okay? Because it's compared to this CH3, it's you know, significantly further away from carbonyl group. Carbonyl group is the key electron withdrawing group here, okay? And the carbon 13 is similar, and the signature band of carbon 13 and the carbonyl compound is the carbonyl carbon itself. It's always appear at the extremely high chemical shift value, generally around 200 ppm or a bit even higher, because it's very low electron density on the carbonyl carbon. It's very electrophilic, right? So that is a signature one, okay? Then the remaining part, the carbons, okay, it depends on its position to the carbonyl group. So if they are shorter distance to carbonyl group, it will have a higher chemical shift value. So the you know, these two carbons, okay, they have the highest chemical shift value, okay. But which carbon has even a bit higher chemical shift value? The left side one or right side one? The right side one. This one's a bit higher, okay. And this one should be this, okay, because again, CH3 will be slightly less electron withdrawing than CH2. So the difference between these two guys is that if the left side is CH2, right? One side is carbonyl, the other is CH3, okay? But the right side is CH2, the one side is carbonyl, it's the same, okay? But the other side is CH2. CH2 is slightly more electron withdrawing than CH3. Okay? Now remaining should be easy. You know, let's come to assignment. So this CH2 should be this, okay? And then the and then this CH2 should be this, okay? And then the CH3, obviously the CH3 gonna be this, okay? And the, you know, the CH3 has the lowest chemical shift value is this one. Okay? So let me see the color. This CH3 should be this. Okay? Apply the same rule we have in chapter 14. Carbon 13 and NMR mostly reflect electron density, inductive effect, judged by distance. Okay? UV visible, really not much to talk about. Mass spectrometry, you know, the basically you look at the possible, you know, this fragmentation process. Molecular ion peak of ketonaldehyde usually are pretty intense. And if in a molecular ion, if you look at ketonaldehyde, it's always going to be the you know, oxygen to be losing one of its lone pair electrons. Because that's the electron at the highest energy orbital, non-bonding orbital. That's the highest energy, easy to lose. Then this guy could undergo fragmentation process. So how do you do that? How you understand this fragmentation process? Okay. So basically, okay, on the form stable, most stable carbocation. So this electron can come here, okay. This electron can come here, then the electron come here. Okay? So that gives you a carbocation. Every atom satisfies octet group. That's called ethylene cation, and the break up losing a radical. All right, I think here concludes the chapter 18. So the maybe we can have a break of 7-8 minutes, and then we could continue chapter 19. And the exam, obviously, we're gonna be have it next week as scheduled.